Hello. So last time we defined some necessary concepts for the graph. And main motivation for those concepts and definition is to effectively deal with the problems that we encounter. And we encounter various problems, and which all relate to this one object, which is we defined as a graph. And one of the most obvious such problem was when there was some network and there was some connections between them. It could be some, say, metro map, and each vertex is stop, and its edges are the metro line between them. And there you are at somewhere, and then you move along these edges, and your goal is usually to get somewhere. There are many variations for this. This vertex could be city, and then edges could be road. And also, it's not that you are moving. You might send something, you might transport something. Then you might be interested in how much you can transport, and then whether you can distribute them where there are many variations. But in this setup, again, there are natural concepts which arise. So in this very basic model, what we care about is that there are certain starting point and ending point, and you want to move from here, and somehow, you get there. And while you're getting there, you move along the edges and then move along the edges. And these are very basic and natural concepts. So we want to give some names for this property or some substructure. Then it will be very convenient for us later when we deal with the problems. So here, what's the point? So you are at here, and then you are moving along the edges. Then your location changes, and your location changes, your location changes, and your location changes. And this is actually a sequence of vertices where the the consecutive vertices on the sequence are connected by edges. So also it can be seen as a sequence of edges. So we define this. So our picture is that you are at somewhere, and then you are walking along these edges. So one natural name we give is walk. So we say a walk in graph G is a sequence, say B1, B2, BK, or vertices. And also it's a sequence of edges. So it consists of the vertices and edges. So this is actually a graph, which is subgraph of the original graph G. And this is what we called a walk. And especially we give a name to this walk in that the walk is closed if P1 and Pk are the same. So if you come back to where you are, this is a special type of work, so we call it a closed walk. This is also important. In many cases, you might want to visit somewhere and then come back to the place where you started. In everyday life, we start at home and then we go somewhere, and then come back to home. So this is natural content. And if you think about it, in this walk, you could go here, and then here, and then here, and then come back to here. and come here again, and go here, go here. This could be possible, but somehow you feel that this is inefficient and redundant. For example, here you visited here twice, and then you are passing through this edge twice. You might say that if this is our goal, then why not just go here this way? In real life, also, if you use navigation, then you wanted navigation to suggest you the best route instead of taking longer time, or instead of the route which take you to the same place two, 3 times. So we want to also give name to those more efficient work, not just any work. So we say that work is a trail. Maybe let me highlight this with the blue. This is a trail if all edges v1, v2, v2, v3, vk minus 1, vk are distinct. So none of them are same. So we don't traverse the same edge twice. Then you say that this is a trail, and a closed trail is called a circuit. So a closed walk is also a trail, then we call it circuit. So trail could be something like this, for example. You go this way. But still, and circuit is more this. You start from here and then you come back. However, still you feel that this is not as efficient as possible. At least, I mean, you didn't traverse the same, I mean, edges twice. Edge-wise, this is efficient. However, from here, why do you go in this way? If you just want to get there, you just pass through. So if edge is not repeated, we give a name of trail, and more efficient structure is the structure or walk where the vertices are not repetitive. This is what we call as a path. If all we want to be k are distinct. And we said a closed walk, we want to be k, where we want to be k minus 1. So the last one, vk, has to be same with v1 because this is a closed walk. Are distinct is called a cycle. And we say that k minus 1, which is the number of edges, is the length of the walk. So what's the length of this walk? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This walk, 1, 2, 3, 4, 5, 6, 7. So that's the length of the walk. So recall that our goal was to define this concept which provides connection, which is a walk. And we want to understand the work and how these works, I mean, are formed, and then what property can we get from here. But as I mentioned before, this work seems a bit complicated. So from the look, I mean, it could be quite complicated looking, but this path is more intuitively straightforward to us. It's just one line with some dots in the middle because all the vertices are non-repetitive. So to our understanding, dealing with paths is more intuitively clear than dealing with works. But in fact, even if we define work as the object we wanted to deal with in the connectivity problem, we can actually see that the path is the actual essential object that we want to be deal with. Mm, because, okay, maybe, so, because of the, say, following lemma, let me say proposition. If you have a work from U to V contains a path from U to V. So we can prove this proposition. And if we know this proposition, then what do we get? So we, as I mentioned, we want to deal with this kind of connectivity problem. So from U to V, the important property is whether we can start from U and then end at V. So existence of a work from U to V is what we are interested in. But if this proposition is true, then what do we know? We don't have to care about the existence of a work from U to V because we can just be interested in the existence of paths from U to V because this proposition shows that they're equivalent. So this says that if there exists a path, I mean, work from U to V, then there exists a path from U to V. And then the converse is true because path is a work. So existence of work from U to V is equivalent with existence of path from U to V. So this proposition allows us to give the following definition. So we say that a graph G is connected. So we want to say this is connected, which is a useful concept and useful and basic concept. If for all pairs U and V, there is a path in G from U to V. And especially we say that a subgraph of G is component, or sometimes to be more specific, connected component of G is a connected subgraph, which is maximal with respect to the inclusion. So for example, if you have this graph, then it's easy to check that this is a component, this is a component, this is a component, this is a component. So this is a connected graph, connected subgraph, but it is not maximal with respect to the inclusion because you can include this one vertex more and two edges to get the connected component. And for example, this subgraph is not a connected component because you can include these edges. So this is not maximal. But on the other hand, this is not a connected component because this is, no matter what other edges or vertices of G you add, it's never a connected subgraph. So it's easy to check. And why do we care about this connected component? Because as you see here, any graph G is disjoint union of connected graph. So understanding connected graph provides an understanding of arbitrary graph. For that, let's define what disjoint union means. So for two graph G, which consists of the vertex set V and the edge set it, and H, which consists of vertex set V prime and edge set E prime, we say the disjoint union of G and H denotes the graph B, say disjoint union B prime, and E disjoint union of E prime, where B and B prime are considered as disjoint set. So this is disjoint union of those four graphs. So again, this proposition provides the motivation for this. This proposition justifies this definition as a path instead of work here. Then we are interested in component. So we are interested in studying connected graph because that provides the understanding of arbitrary graph because arbitrary graph is disjoint union of connected graph. So let's prove this proposition. So every walk from U to B contains a path from U to B. How do we prove it? So in many times we are gonna use minimality or maximality. We will consider certain minimal object or certain maximal object with respect to certain concept. So we define what minimal in what sense, minimal in what, maximal in what sense, and then we will take advantage of the property that the maximal or minimal object naturally has. So we take, so what's our goal? So we want to show that if you have a work, then there must be a path. But the definition of path was to take the most efficient work, right? And here, most efficient is the shortest one. So we follow that intuition. So we take a shortest walk from U to B. So we write UB walk, indicating it starts from U and then it ends at V. Let's say this UB walk is W, which is B1 to BK. And and we want to show that this is actually a path. If this is not path, then what happens? And there is I and J such that the Bi and Bj are same for some I smaller than J, and both of them are between 1 and K. They are in bracket K. Then what happened? Then if you draw the picture, then you will get it. So Vi and Vj, it's same. Then instead of going this way, you might take just this way. Then again, you take V1 to Vi minus 1, and then instead of going to Vi plus 1, you directly go to Vj plus 1, Vk. Because these two are same. So this forms an edge, this forms an edge. So this forms a what? A shorter UV walk, which is a contradiction to the choice. Hence, V1 to Vk are all distinct. So W is the desired path. Yeah, it is the path from U to V. So actually this proposition only also works for directed graph. And for directed graph, you can define directed walk and directed paths in the natural way. And you can check yourself that you can actually use this proof to prove that. So basically, this defines connected graph. And then we want to study about the connected graph. And okay, so what we will do is we have learned many concepts and we will learn more concepts. And then we want to study about the interactions between them. And for that purpose, maybe it's a good time to give you some examples of what we are gonna learn, what kind of statements we are gonna learn. Maybe we will do that in the next video.